Welcome back to the channel. Hope everybody's doing well, and in today's video I'm going to be testing out this little temperature transmitter that you see down in the bottom of the picture here. This is what we refer to as a puck style transmitter. You can also get them in a DIN rail mounted style for mounting into a panel, whereas this one would mount into the actual sensor head out on plant and convert the signal there and then before transmitting it out to the control panel. If you've not seen that kind of setup before, very briefly, this is the type of sensor that you would have out. This is the sensor element here. It would actually sit inside a thermal well, inside a tank or a pipe or a manifold or something like that. If I take the terminal cover off, you can see this just has a terminal block there at this moment in time. So the sensor head comes out to this. You would then take this into the local readout or local control panel. If you're going over short distances, that's fine. If you're going over longer distances, you can get specialist cabling for, this is an RTD type PT100, so you can get a specialist cable that would extend this or extend a thermocouple style sensor. Instead of that, what you can do is take out this terminal block, replace it with this little transmitter puck here, and then this will convert the PT100 signal directly into either a 4 to 20 milliamp or a 0 to 10 volt signal, and then you can transmit that over long distances using standard twisted pair wiring. So this particular puck that I have here, this is actually from Amazon. It comes in at £16.49. In contrast, a puck style transmitter from somebody like Omega would be £96. Another one from Anderson Hauser is £126. So usually the ones that I use out in industry are way more expensive than this little device, so it'll be interesting to see how it performs. The manufacturer for this is actually Sourcing Map. It's a PT100 sensor, and it takes an auxiliary supply of 24 volts in, which I'm getting from my Keysight over there. You see that's set to 24 volts and we're 18.4 milliamps. Accuracy on this is 0.2% full scale for a 0 to 10 volt output. So for each of the measurement steps that I'm making, there's a plus or minus 20 millivolt tolerance. Very briefly, this is the test setup that I have. This is the setup that I would use prior to obtaining all of these process calibrators that I've been looking at over previous videos. This is a resistance decade box from Time Electronics. It's the model 1041, and I have the U1461A currently in voltage mode there. Overall, this test setup, these two instruments, they come in at £1,552. So pretty expensive, and that is actually obsolete at this moment in time. On its own, that was £1,089, and this is £462. So my actual test method, since this is a PT100 sensor on this is what the resistance decade box is emulating. You can get resistance tables for PT100 sensors, and that will give you the equivalent resistance for the sensor depending upon its temperature. You then select the temperature points and you can find out what your resistance setting will need to be to emulate those temperature points. This transmitter here, I didn't mention that, I should have done. This is actually minus 50 to 200 degrees centigrade. So at this moment in time, I have set the resistance box to 80.11 ohms to simulate minus 50 degrees C. If you look at the sensor table, that should actually be 80.3068 ohms to emulate minus 50 degrees C. However, this little resistance box does have its own internal residual resistance plus the resistance of these leads onto the puck there. So as a consequence, what I've had to do is measure each of the test points using the DMM 7510 and find out what I need to set this resistance box to get me the correct resistance value at this point here. So I've got 10 test points, 0 to 10 volts in 1 volt intervals to cover the output of this transmitter. And what I'm also going to do is just time myself to see how long it takes using this test methodology. So we are currently set up on minus 50 and we are reading 0.004 volts. We'll start our clock off And we'll put him in there. And then minus 25. That's 89.99. So that should be 90.192 for the actual resistance, but it's 89.99. I'll set the box 2 to get that. So that's giving me a reading of 1.009. 0 is 100 ohms, but I need to set this to 99.81, and that should give me 2 volts out, which is 2.015, so that's still within spec. 25 degrees C should give me 3 volts out, and I'm 109.62. And that is 3.018. 4 volts is 50 degrees C, which is 119.26. And that is 4.018, so we are just within spec. We're at the top end there. It should be 4.020 would be the maximum. 75 degrees C for 5 volts is 128.81. 5.018. 6 volts is 100 degrees C, and I need 138.34. That's 6.019. And 125 degrees C is 147.78. 7.01. So I have actually lost a decimal point on the Keysight there, which is worth remembering. 8 volts is 150 degrees C and 157.09. All the way there. That's 8.01. 9 volts will be 166.40. And that should be 175 degrees C, and we are 9.01. Yeah, I'll say 9.01. And the final one, 10 volts is full scale, 200 degrees C, should be 175.64 on my resistance box. And we are smack on 10 volts. So there you have it. Let's go to my little clock. And that has taken me 3 minutes 45 seconds to go through those test points. In all honesty, if you're doing this out in the field, you would probably only have 3 or 4 test points. You wouldn't do this many. But obviously what I haven't included in this is the time taken to get the setting points on this decade box. So it's worth bearing that in mind as well. But that's that all tested. I will now put up the results sheet from this, and this is the full table. So on the left hand side here we've got the voltage coming out of the transmitter itself in its 1 volt steps. You've then got the equivalent temperature values there in degrees C and then degrees Fahrenheit. So the nominal ohms from conversion table, that 4th column there, that's the resistance value from the conversion table I need to emulate, to put into this transmitter to emulate the temperature setting there. And the next 2 columns are what I've measured with the DMM to get the right value in this resistance box. So if we look at the first line there, 0 volts coming out, minus 50 degrees C, it should be 80.3068 ohms. I set my resistance box to 80.11 ohms, and when measured with the DMM 7510, that gave me 80.2903 ohms. So that column for the DMM 7510 always need to be as close as they can be to the nominal ohms from the conversion table. You see they don't match exactly. It's just the way it is. You can't get exact matches, so you do have to live with a little bit of error. Then we've got our U1461A reading. As you can see, everything is within the minimum and maximum values on the next two columns there. You do in the middle, it is going up, isn't it? It's 3.018. What are we? 25, 50, 75, 100 degrees C. They're all heading towards the max tolerance values, really. But as I said, they are all within the plus or minus 20 millivolts, so no problems in that respect. So yeah, that'll be the end of this video. The intention of this was to give myself a little base model, so in future videos I can look at the different test methodologies now available to me with these process calibrators I have, and see if there's an improvement in either accuracy or if it's quicker to do the actual measurements themselves. So there you go, thanks for watching, hope you found it useful, and I'll see you again in the next one.